Hey, what's up, Chem Peeps? What in the heck are we gonna do in this video? In this vid, we want to be able to calculate the partial pressure of a gas in a mixture of gases. As always, breaking it down. 1. You want to be able to calculate what's called the mole fraction of a gas. 2. You want to use the mole fraction of a gas to calculate the partial pressure of a gas. So once again, we're just cranking it up a little bit, moving on from Dalton's law of partial pressures to the next level. Alright, so recognize that many gas samples are not pure, but are mixtures of gases. Air, for example, is a mixture containing nitrogen, oxygen, argon, carbon dioxide, and a few other gases in trace amounts. Mixtures of gases are everywhere. You're swimming through one right now. Now, in certain applications, you can think of the mixture as just one gas. So, for example, even though air is a mixture, we can measure the pressure, the volume, and the temperature of air as if it were a pure gas, if it were a pure substance. And we can then calculate the number of moles of molecules in an air sample, knowing pressure, volume, and temperature, even though they're different molecules. So let's take a look at this thrilling simulation one more time. Let's say I were to put 50 molecules of this heavy species, this purple gas, into the container. Note that the pressure is about 0.2, 0.3 atmospheres. If I add an equal amount of a different gas, notice that the pressure roughly doubles. Half of that pressure is coming from the purple gas, the other half is coming from the red gas. And it's important to know that even though this is a mixture of two different gases, if you know the volume of the gas, if you know the temperature of the gas, and if you know the pressure, the combined pressure of the gas, you can calculate the number of total moles of gas molecules in that container, even though they're different gases. What that means for us is we're going to crank it up a notch and take Dalton's law of partial pressures and combine it with the ideal gas law when we're working with mixtures of gases. Again, keep in mind that even though we're working with a mixture of gases, you can treat it as one gas. So remember that Dalton's law of partial pressures indicates that the total pressure of a sample of a mixture of gases is equal to the sum of the individual partial pressures. And while you could determine the number of moles of each of the individual gases and plug it separately into the ideal gas law equation, if you treat the mixture as if it were just one gas, all you need to do is know the total number of moles and plug it into the Pivnert equation one time. Alright, so the big point of this video was to talk about how we could use what's called mole fractions to determine partial pressures of gases. So first, recognize when we talk about partial pressures, what we're talking about is what is the part of the total pressure that's being contributed from one of the gases in that mixture. So what is the partial pressure of the red gas contributing to the total pressure of approximately 0.5 atmospheres? Or what's the partial pressure of the purple gas contributing to the total pressure of 0.5 atmospheres? And it turns out you can determine that partial pressure of just one of the gases in a mixture by determining what's called its mole fraction and multiplying it by the total pressure. And if you're looking for just the mole fraction, it's simply the number of moles of the component, or the moles of that one gas in the mixture, divided by the total number of moles in the mixture. Alright, so let's take a look at a quick example to give us a better understanding of the types of problems that we're going to have to solve using mole fractions and partial pressures. A gas mixture being used to simulate the atmosphere of another planet consists of 333 milligrams of methane, 172 milligrams of argon, and 251 milligrams of nitrogen. Calculate the mole fraction of methane in the mixture. Alright, so first let's recall what mole fraction means. The mole fraction of methane, or CH4, is equal to the number of moles of methane over total moles of gas. So the first thing I need to do is determine the number of moles of methane and then determine the total number of moles of gas in my sample. So first thing I'm going to do is I'm going to take my 333 milligrams of methane and convert that to moles. Boom. I'm going to use the following dimensional analysis and the molar mass of methane, 16.042, which came from the periodic table. I'm going to do the same thing with my 172 milligrams of argon. Boom. Once again, I'm going to create a dimensional analysis setup to convert my grams of argon to moles of argon using its molar mass from the periodic table. And then finally, we'll do the same thing with nitrogen. being super careful to recognize that nitrogen is one of our diatomic gases. Boom. One more dimensional analysis setup. Now just a quick jump to our good friend calculator. 0.333 times 1, enter, divided by 16.042, enter. 0.0208 moles of methane. 0.172 times 1, enter, divided by 39.95, enter. 0.00431 moles of argon. 0.251 times 1, enter, divided by 28.02, enter. 0.00896 moles of nitrogen gas. All right, so if we want the mole fraction of methane, it's just going to be the number of moles of methane, 0.0208, over the total number of moles in the mixture. So 0.0208 plus 0.00431 plus 0.00896, enter. Our total number of moles in the mixture, 0.0341 moles. Which means our mole fraction, 0.0208 divided by our total number of moles, enter. Our mole fraction is 0.611. Boom. What does this mean? The majority of the pressure exerted in that mixture is going to come from the methane. So, follow-up question, if the total pressure of the mixture is measured to be 734 millimeters mercury, what is the partial pressure exerted by the methane? Well, remember that the partial pressure of the methane gas is equal to the total pressure times the mole fraction. And the mole fraction is represented using this large letter X. Total pressure, 734 millimeters mercury. Mole fraction, 0.611. That means the partial pressure of just the methane in that mixture, 734 times 0.611, is 448 millimeters mercury is the partial pressure contributed by the methane. Boom. And we are done.